Imagine a detective, right? They walk into a bloody crime scene, and instead of actually looking around at the evidence, they just close their eyes tight and insist on reading the police report instead.
Yeah, that would be completely absurd. You'd fire that detective immediately.
Exactly. But believe it or not, that is basically exactly how today's most advanced AI models behave when you ask them to solve a really complex problem. Welcome to the deep dive.
It's honestly a pretty glaring blind spot,
Hmm.
especially for these systems that we are, you know, increasingly trusting to process the whole world for us.
Right, because we're relying on them more and more every day.
Exactly. And the data shows that when we ask an AI to untangle a puzzle that requires looking at images, reading documents, connecting all these dots, they fundamentally prefer to just ignore the visual evidence entirely, unless they are explicitly ordered to look at it.
Which is, frankly, terrifying if you're using that system to do anything remotely important. Today, we are unpacking a fascinating paper from researchers at UIUC, Meta, IBM, and Stony Brook, and they're detailing a brand new benchmark called MC Search.
Yeah, MC Search it's a huge step forward.
Okay, let's unpack this. Our mission today is to figure out how artificial intelligence is evolving from, those simple retrieve and generate bots that just spit out a quick trivia fact.
Like a glorified search bar.
Right, exactly. From that, into these sophisticated, what they call agentic multimodal reasoning sleuths, and more importantly, how we actually measure if they're any good at doing all that heavy lifting.
Because the measuring part is actually where the whole system has been failing. To really appreciate what these researchers built, we have to look at the cracks in the foundation of how we currently evaluate AI.
So how are we testing them right now?
Well, we use these existing benchmarks. You might have heard names like OKVQA or WebQA, and they operate on what's called a fixed retrieve then generate paradigm.
Okay, which is a highly technical way of saying what exactly?
It basically means the current tests they're like an open book pop quiz where the teacher has already gone in and highlighted the exact sentence you need to read.
Wow, okay. So it's barely testing their reasoning at all.
Barely. Usually it takes maybe one or two really shallow steps, they call them hops, to just get the answer. There's no real investigative work happening.
And I think I read that it's even worse when it comes to images, right?
Absolutely.
Oh.
I take it a step further. It's not just that the answers are handed to them. The visual data itself is fundamentally dumbed down in these old tests.
Yeah.
So in those older benchmarks, images are usually just compressed down into simple text captions behind the scenes.
Wait, so the AI isn't even really looking at the picture?
No, not really. If you show the AI a really complex photograph of like a bustling city street, it isn't seeing the nuances of the architecture or how the lighting hits the buildings. It's really just reading a hidden text string that says, cars on a road.
But that completely defeats the purpose. If I ask an AI to plan a historically accurate vacation based on some random photo I took of a cathedral in Europe, I don't want it to just read a generic caption.
Right. You need it to act like it's writing a real research paper.
Exactly. Cross-referencing the architecture with historical text, finding the exact location, building a route. Because real-world questions from you, the listener, they're inherently messy. They are ambiguous.
And that ambiguity is exactly why the future of AI relies on something called iterative ask decomposition.
Iterative ask decomposition. Okay, break that down for us.
So an advanced model needs to look at a really complex prompt from a user, break it down into a sequence of smaller, manageable sub-questions, and then adaptively search for those answers.
So it's like making its own to-do list as it goes.
Pretty much. And if its first search returns a dead end or maybe just an incomplete picture, it needs the cognitive awareness to realize, oh, this didn't work. I need to pivot and formulate a new search query based on what I just learned.
But because the old tests were just handing the AI the highlighted answers, the researchers realized they had to build an entirely new obstacle course.
Right, one where the AI couldn't cheat.
Yeah, where it actually had to prove its ability to do this deep adaptive library research. And that is what MC Search is.
And the scale of this new benchmark is, it's unprecedented for this specific type of task, what we call agentic multimodal RAG, or retrieval augmented generation.
The numbers in the paper were huge.
Yeah, they compiled 3,333 high-quality, really complex examples. And on average, a single query in this benchmark requires 3.7 distinct hops to solve.
So it's not just one quick Google search, it's 4 separate logical leaps.
Exactly. And the most important part is they aren't just grading the final answer. They are grading the entire long step-by-step annotated reasoning chain the AI uses to actually get there.
Which makes sense. You want to see the math, not just the final number. So to map out how these reasoning chains work, the researchers tested the AIs across 5 distinct cognitive challenges. They call them topologies.
I love it, geez, yeah.
So instead of just listing them off, let's walk through how they escalate in difficulty, because it gets wild. Let's start with the baseline. If an AI is just doing a complex text-based search, what does that look like?
Well, the baseline is what they call the text-only chain. So everything exists purely in the realm of the written word here.
Okay. Pretty standard for a language model.
Right. So, for example, the AI is asked to research the Bentley Mulsanne car. It has to find its manufacturing dates, then dig up its specific engine specs, and then locate information about the special WO edition.
Oh, the one that features a piece of a personal crankshaft, right?
Yes, exactly. So it's a very linear, very deep dive, but entirely through text documents.
Okay, text is totally familiar territory for these models. But what happens when the prompt kicks off with a visual and the AI has zero written context to start with?
That's the image-initiated chain. So the benchmark hands the AI an image of a painting, no caption, and asks a massive multi-part question. Something like, what biblical scene featuring Archangel Gabriel is depicted here? Where is this painting currently held? When and for how much was it acquired?
Oh my God.
And what historical significance did this acquisition represent for the artist regarding American museums?
I mean, I would struggle to answer that if you gave me a full weekend and a library card. How does the AI even start?
It requires 4 very specific logical leaps. First, a purely visual search. It analyzes the pixels and identifies the painting as the Annunciation.
Okay, so it knows the painting. Then what?
Second, it has to pivot to text. It searches the internet to find out the painting is currently at the Philadelphia Museum of Art.
Got it.
Third, it does another text search to discover it was bought in 1899 for $750. And finally, a fourth search to find the historical context confirming this was the artist Henry Ossawa Tanner's first work ever purchased by an American museum.
Wow. Starting from pure visual pixels and ending up at a deep, nuanced historical fact. That is incredible. I can see how an image kicks off a text search. But does it work in reverse? Like, can an AI read a claim and then go out and seek visual proof?
It has to, yeah, and that's the text-initiated chain. So in this topology, the benchmark feeds the AI a piece of text describing Solvang, California as this, bit of Denmark tucked into the American landscape.
Okay.
But the prompt asks for visual confirmation of that claim. So the AI has to transition from reading to seeing. It formulates the search for images of Solvang, scans those images, and has to visually identify Danish architecture.
Like looking for a windmill or something.
Exactly. It literally has to find a large windmill in the photos to validate what it read in the text.
Okay, that makes sense sequentially. You read, then you look. Or you look, then you read. But what happens when the AI has to do both at the exact same time?
This is where we really see the models start to sweat. They call it the parallel image-text fork, and it requires simultaneous processing.
How does that work?
Well, the benchmark shows the AI an image of an antique mandolin. But at the exact same time, it feeds the AI a dense text about Pasquale Venaccia's 1835 innovation in string design.
Let me guess. The AI has to figure out how those two totally different inputs are connected.
Bingo. It has to connect the visual evidence, identifying that the mandolin in the image has steel strings with the text, which explains that steel strings created higher tension.
Oh, I see.
And because of that higher tension, the text explains a structural change was required. They had to deepen the bowl of the instrument for better resonance and support.
That is just, it's like asking the AI to rub its stomach and pat its head at the same time. It has to hold visual memory in one active processing buffer, read historical text in another buffer, and figure out the causality between the two.
It's a massive cognitive load.
And that leaves the final challenge, right, which completely removes text from the initial equation.
Yep, the multi-images fork. So imagine the AI is shown 2 different architectural photos side by side. One is the Epcot Canada Pavilion, which has this very steep, multi-tiered roof.
Okay.
The other is the Epcot Morocco Pavilion, characterized by a tall, slender tower. The AI has to visually compare the two, realize the user's question is asking about the pavilion with the slender tower centerpiece.
Identifying Morocco just by looking at it.
Right. And then once it makes that visual identification, it pivots to text to find out the Morocco Pavilion opened in 1984.
Okay, so when I hear you lay out these long chains of reasoning, finding a painting, then finding the museum, then finding the price, the skeptic in me, It just has to hit the pause button.
Oh, absolutely. I know where you're going with this.
Right, because we know for a fact that large language models hallucinate constantly. They are incredibly good at sounding super confident while making things up entirely out of thin air.
They are chronic people pleasers.
Yeah. So how do we know the AI didn't just stumble onto the $18.99 purchase price of that painting by taking a lucky guess without actually following all those logical steps?
The researchers anticipated that exact skepticism. Because if you build a complex maze, you need a way to ensure the runner didn't just, teleport to the finish line.
Right.
So they built a ruthless, mathematically strict grader to score the AI's process. They call it AVE. That stands for hopwise attribution and verification of evidence.
Hey, VE. Okay, how does a mathematical grader actually check a model's logic? That sounds impossible.
What's fascinating here is how HAVI acts as this strict filter against hallucinations and lucky guesses. It evaluates every single intermediate step an AI takes based on two specific criteria. The first one is context utility.
Context utility, what does that mean in practice?
Mathematically, HAVI runs a simulation. It basically asks, if I completely delete the clue the AI found in step 2, does the AI's probability of generating the correct final answer drop?
Oh, wow.
Yeah. If removing that middle clue doesn't change the final outcome at all, HAVI determines that step was just useless fluff.
So it penalizes the AI for padding its answer to sound smart. If a clue wasn't strictly necessary to solve the puzzle, it just gets thrown out.
Precisely. And the second criterion HAVI uses is the navigational role.
Okay, and what is that?
Well, sometimes a step doesn't directly answer the final question, but it provides an essential keyword needed to unlock the next search. So HAVI actually checks the search queries the AI generates.
Like looking at its search history.
Exactly. It checks, do the exact entities and keywords discovered in step 1 actually appear in the search bar for step 2?
Oh, that's brilliant.
If a step doesn't directly help answer the question, and it doesn't pass the baton to the next search query, AVE flags it as a hallucination or a broken logical chain, and it just straight up fails the model.
That is an incredibly rigorous gauntlet. Okay, so the obstacle course is set. The HAV grader is holding a very unforgiving stopwatch. When the researchers forced the top models, we're talking Gemini, GPT-4o, Claude, Quinn, when they forced them to run this maze, what did the report card actually look like?
It was pretty revealing, because they looked far beyond just whether the final answer was correct. They introduced process-level metrics.
Like what?
One is hit per step, meaning at step 3, did the AI retrieve the exact, verified golden piece of evidence it was supposed to? Another is rollout deviation.
Meaning, did it wander off the path?
Right. Did the AI take way too many unnecessary steps, or did it under-retrieve and skip crucial logical leaps?
So what did the data actually show? Who won?
Well, essentially, the models do pretty well up to 3 hops. They can hold a train of thought for about 3 steps. But once a query requires 4 or 5 hops, performance absolutely plummets across the board for every single model.
Every single one. That is super revealing. It's like a hard cognitive breaking point.
Exactly. The compounding difficulty of sustaining that long horizon reasoning, juggling previous clues while actively searching for new ones, it simply overwhelms their attention mechanisms.
Honestly, it perfectly mirrors the human experience of going down a Wikipedia rabbit hole.
Oh, 100%.
You click on an article about a movie, which links to an actor, which links to a historical event they were in a play about, and 3 clicks deep, you are staring at a page about 14th century agriculture, and you have completely forgotten what your original question was.
The AI is experiencing the exact same loss of focus. Its attention mechanisms just get diluted, and the data shows us exactly which topologies trip them up the most. Across all the models tested, the absolute hardest path was the parallel image text fork.
The rubbing the stomach and patting the head problem. The mandolin example.
Yes. The models fundamentally struggle to juggle visual and text branches simultaneously. If they allocate computing power to parsing the text about the 1835 string innovation, their active memory literally drops the visual processing of the steel strings.
Like they just forget what they're looking at.
Precisely. The error rates are staggering here. There was an 84.7% rate of retrieval failure.
Wow. Meaning they just flat out failed to find the next clue.
Yep. And a 75.8% rate of hallucinated entities. Meaning when they got lost and couldn't find the clue, they just started making things up to fill the gap.
If you're listening to this and thinking, well, I just use AI to draft emails or summarize my meeting notes, why does it matter if it can recognize the strings on a 19th century mandolin? It matters because this is about the underlying architecture of trust.
That is the perfect way to put it.
If the model panics and hallucinates when it gets confused, how can you trust it with your financial data or your really important business research?
And that trust requires understanding how an AI searches. Analyzing these errors revealed what I like to call the Goldilocks zone of retrieval.
The Goldilocks zone. I like that.
The researchers mapped out the consequences of an AI over-searching versus under-searching. Severe under-retrieval is always fatal.
Obviously. If you skip a step like failing to identify the name of a museum, you literally cannot search for what year the museum bought the painting. The chain is permanently broken.
Right. You can't solve a mystery if you just walk right past the murder weapon. But what happens if the AI over-retrieves? What if it gathers too much information?
Yeah, does it get confused?
This is the fascinating part. Moderate over-retrieval actually helps the models recover from early mistakes.
Really?
Yeah. Taking one or two extra, slightly unnecessary steps acts as a buffer. It casts a wider contextual net, which sometimes gives the AI the extra grounding it needs to find its footing and get back on the right path.
Okay, but I have to imagine there's a tipping point, right? Where that wider net just hauls in garbage.
A very strict tipping point. If the model over-retrieves too much, taking 4 or more extra tangential steps, the signal-to-noise ratio is completely destroyed.
It just drowns in the noise.
Exactly. The extra context floods its attention mechanism, it drowns in irrelevant data, and it fails just as spectacularly as if it had missed the clue entirely. It needs the amount of context to be just right.
Hence the Goldilocks zone.
Exactly.
Well, aside from getting lost in the weeds of over-searching, the researchers uncovered something else. And here's where it gets really interesting, because this goes back to that blind detective we talked about at the very beginning of the deep dive. It's a massive fundamental flaw in how these models process reality.
We're talking about the modality gap.
Yes, the modality gap.
Right.
The data explicitly shows that these models are heavily biased toward the written word. If a user's prompt does not contain a specific direct command telling the AI to look at the image, the models almost entirely ignore the visual evidence sitting right in front of them.
The drop-off is severe. Just look at the intern VL model evaluated in this study. When an image was explicitly mentioned in the text prompt, like, hey, look at this picture, its image retrieval coverage was about 63%.
Okay, not bad.
But when an image wasn't explicitly mentioned, even though looking at the image was entirely necessary to solve the problem, its use of visual evidence plummeted to less than 1%.
Less than 1%? That is insane. It is functionally blind unless you explicitly command it to open its eyes. Why is that happening? Why would an advanced multimodal AI just ignore half of its own sensory input?
It exposes a deep bias in their underlying training architecture. You have to remember, these multimodal large language models are built on top of foundation models that were trained on vast oceans of text from the internet.
Right, text is what they know.
Text is their comfort zone.
Mm-hmm.
It is neurologically, so to speak, where they feel safest. Integrating visual data requires a cognitive leap that their internal weights are hesitant to trigger without a direct, undeniable command.
But the researchers at UIUC, Meta, IBM, and Stony Brook, they didn't just write a paper exposing these flaws and call it a day. They actually figured out a way to fundamentally alter the AI's behavior. They created a training framework called Search Align.
Yeah, and this is where MC Search transitions from being just a diagnostic test into an actual curriculum. The researchers took open source models like Quinn and Intern VL and performed what's called supervised fine-tuning.
How does that actually work mechanically? Like, how do you force an AI to change its behavior like that?
Well, instead of just rewarding the AI at the very end for guessing the right answer, they forced the AI to train specifically on those verified golden reasoning chains we talked about earlier.
The perfect step-by-step paths.
Exactly. During this fine-tuning, they tweak the model's underlying mathematical weights. If the AI skips a step, or if it hallucinates a path, or if it ignores an image entirely, the training algorithm adjusts its internal neural pathways.
So it's computational discipline.
Yes. It's literally penalizing that specific behavior computationally, so the model is far less likely to make that bad logical leap again. They force the AI to show its work, step by step.
And the crazy part is, it actually worked. By computationally penalizing that lazy behavior, the open source models saw massive performance jumps. The Quinn model jumped nearly 14% in its comprehensive accuracy metric.
That is a huge leap for a benchmark this hard.
Right, meaning it was not only getting the answers right more often, but it was providing complete, well-reasoned answers. And even more importantly, the process errors dropped. The modality mismatch where it stubbornly used text when it should have looked at an image that dropped significantly.
And step omissions, skipping those crucial logical leaps, also plummeted.
It's amazing, by forcing them to practice the rigorous process of investigation, the AIs actually became better detectives.
They really did. And this shifts the entire paradigm of future AI development.
Yeah.
Training the next generation of AI shouldn't just be about scraping more of the internet to build bigger static databases of facts.
Right, it's not just about memorization anymore.
Exactly. It has to be about teaching the AI how to plan. It's about teaching it how to evaluate a problem, break it down into pieces, and actively choose the right tools, whether that's a text search, an image scan, or cross-referencing two different data sets for the specific job at hand.
Let's take a step back and just look at the territory we've covered today, because we are mapping out the very frontier of how machines reason. We are watching the real-time transition from AIs that simply recite prepackaged knowledge like a calculator to agentic systems that actively search, cross-reference, verify their own clues, and synthesize information.
It's the leap from a digital encyclopedia to an autonomous research assistant.
So what does this all mean? The reason this matters to you is these tools become deeply embedded in everything from your personal devices to global enterprise systems is accountability.
It all comes back to trust.
Right. Whether you are using AI to plan a multi-city international trip or analyze dense financial data, benchmarks like MC Search and training frameworks like SearchAlign are the invisible guardrails. They are the mechanisms that ensure your AI assistant doesn't just confidently deliver a hallucinated, smooth-sounding lie. They ensure it actually knows how to do the rigorous, multi-step investigative work you are relying on it to do.
But, if we connect this to the bigger picture of where artificial intelligence is heading, it leaves us with a rather profound puzzle.
What's that?
Well, we are using tools like SearchAlign to highly optimize these models, right?
Yeah.
Tweaking their internal weights so they perfectly mimic these pre-annotated golden human reasoning chains.
Right, we're teaching them to think like us.
We are successfully teaching them to think exactly the way a human investigative journalist thinks. But by placing these strict, step-by-step human guardrails on the AI's cognitive process, are we inadvertently putting a ceiling on its potential?
Oh, that's an interesting thought.
Think about it. If we computationally punish an AI every single time it deviates from the human way of solving a puzzle, could this strict supervision actually prevent it from discovering entirely new, unintuitive, or even alien ways of solving complex problems, methods that a human mind would never have even thought of?
Wow. We wanted to build the ultimate human detective, but in doing so, we might be stopping it from becoming something else entirely. We'll leave you to mull that over. Until next time.